Okay, so this is, I hope, the final missing recording finally replaced. So I'm narrating this, audio narrating, along with this digital pointer, which I've got here. And so here we are. We talk about the sigma algebra generated by a collection of sets. The idea is to add in as few as possible new sets in order to make a sigma algebra, starting from some given collection. So what happens, what do we know in the way of topologies? I mean, this is a fairly standard thing you can do in maths that works quite frequently. If you start with a collection of subsets of a set X and you want to make a topology on X, then we know that you treat this collection as a subbase, a sort of synthetic subbase. You look at all possible finite intersections of things in that collection of sets, including a sort of degenerate empty intersection, intersection of none, which you treat as being the same thing as X, or you just throw in X anyway, depending on your point of view. And that then gives you a synthetic base for a topology. You have to have those things in your topology because finite intersections have got to be in, the empty set of X have got to be in, you've got no choice about that. So those have got to be in, and then of course it's got to be topology, so you've got to be able to take unions. But it turns out that is a synthetic base for a topology. So you can by looking at the unions of those things, you get the topology on X generated by your collection of subsets curly C. Now that's a sort of concrete way to do it, but there's another way of doing it which is more abstract, where instead you say, let's consider all the possible topologies on X which do include all of these sets in C. So we want all these things in C to be open. That'll be true for certain topologies on X. For example, the discrete topology on X. There's at least one topology that works. If you take all the topologies that work and intersect them, so you take all possible topologies on X with the property that the things in C are all open, then you've got a collection of topologies. If you intersect a collection of topologies on X, you get another topology on X. And it still includes all of these things in C. And it's obviously going to be the smallest or the weakest or the coarsest possible one you can have. And that's how you generate a topology in an abstract way. You can do the same thing with linear subspaces of a vector space when you want to figure out what is a linear span of a subset of a vector space. You can do it concretely by looking at all the possible finite linear combinations of things in the subspace where you always throw in 0 because you've got to do that. So even if you start with the empty set, when you do the linear span, you want to make sure you get a linear subspace. So you've got to throw in 0, which you can think of as the empty sum if necessary. And that's the concrete way to do it. The abstract way to do it is to take all those linear subspaces of your vector space, which include your subset, intersect those, and that will give you the smallest possible linear subspace of your vector space, which includes that subset. And that will be the linear span. So how do you do it in sigma algebras? Well, the concrete approach doesn't work very well unless you use transfinite induction. But the abstract method works perfectly well. And it's based on the following lemma, which says that if you intersect quite a lot of, or some sigma algebras, then you get a sigma algebra. Okay, all of them being sigma algebras on X. Now, it's a surprisingly easy lemma to prove. It's a rather abstract setting, and the consequences are rather surprising, as we're going to see. So you take a set X, you take a non-empty indexing set to avoid the silly issue of what is the empty intersection, though in this case I suppose the empty intersection would have to be the biggest possible sigma algebra on X, I suppose. I'll have to think about it anyway. Something like that. You probably have to get a discrete topology. But we won't bother with that issue. We'll just use a non-empty indexing set to make life easy. And then you take lots of sigma algebras on X and you intersect them. So you say, you look for those sets which are simultaneously in all of the sigma algebras you're looking at. Then when you've done this intersection, you get another sigma algebra on X. So we're looking at a family of collections of subsets of X, and that's quite abstract. But the proof is still very easy. notice the different levels of curliness we're using. These curly Fs are clearly, I use curly letters to mean collections of sets. But we've got an index collection of these. So if I wanted to give a name to the collection of collections, or the family of collections, that would need some further degree of curliness that I'm probably not capable of drawing by hand. Or you could go back to straight letters. Anyway, you can use any notation you like, but it's useful to have something that helps. Right, so let's give a name to the intersection of this collection of sigma-algebras. And of course, I've made an index collection just to make this notation easy. But if you've got a set of sigma-algebras, then you can make your set into an index collection, because you can index a set by itself. And so if you've got a set of sigma-algebras, you can intersect all of those. And that's what we'll be doing in a moment. But the index notation perhaps makes it slightly easier. So what are we doing? So the intersection of these FIs, if you write it, what that means, that's those subsets of X which are in all of the collections. So it's those sets E contained in X which have the property that for all I in the indexing set, E is an element of the sigma-algebra Fi. This could be an uncountable collection of sigma-algebras. That indexing set, I didn't say it was countable, but it is non-empty. So let's see why the empty set is an element of F. Well, for all I in the indexing set, the empty set is in Fi, because Fi is a sigma-algebra on X. And since the empty set is in all of the Fi's, so E equals the empty set satisfies this condition, so the empty set is one of these, so the empty set is in F. Good start. But surprisingly, the rest of the proof is rather similar. We're proving the efficient definition of sigma-algebra here. So we've got the empty set in, now we want to check complements in. So let's take A to be in F. Well, that means that A is in all of the sigma-algebras Fi. And since Fi is a sigma-algebra on X, A complement is also in all of the Fi. You look at any particular I, A is in Fi because it was in F, then A complement's in Fi because Fi is a sigma-algebra. That's true for all I, so A complement's also in F. And that does that one. For the third one, we're going to need to make for all commute with for all. If you've got two for all quantifiers, they commute with each other. So let's have a look at this. You've got a sequence of sets, A1, A2, A3, an infinite sequence of sets, and they're all in this curly F. And we want to show that the union is in. What do we know? Well, since each of these is in F, that means every one of these sets is in every one of the sigma-algebras Fi. Now, it doesn't matter which way around you say that. You can say for all n, and for all n in the natural numbers, and for all I in I, an is in Fi, or you can swap the order of those, because for alls commute with each other. In fact, I've just said it here, for all I in the indexing set and for all natural numbers n, an is in Fi, which is again equivalent. So if you're not happy with moving your quantifiers around, you should check on that, because what you can't do is swap the order of a for all and a there exists. If you ever have a for all and a there exists, it's going to be very different from a there exists followed by a for all. You can't just swap that sort of thing around. Okay. Having said it in this way, we know that since each Fi is a sigma-algebra, and all the an are in Fi, so the union from 1 to infinity of the an is still in Fi, just because Fi is a sigma-algebra. But that's true for all I and I, so this set, the union of the an, is actually in F. And we finished. It's an amazingly easy proof, and the consequences, as I said, are striking. And we're going to look at that now. Or rather, we're going to look at that next. Just an early look at the next slide then. Because of this, you can now define the sigma-algebra generated by a collection of subsets of a set X. And that's the idea. The idea is just to interset all of those sigma-algebras which include your collection C. And we now know that if you intersect lots of sigma-algebras, you'll get a sigma-algebra. So if you intercept all of the sigma-algebras on X that include all the sets in your collection, you're going to get another sigma-algebra which includes all the set in the collection. Starting with this fact, of course, that there is at least one of these, because I did want to intercept a non-empty family of sigma-algebras, but there is one. The discrete topology, the power set of X, is certainly sigma-algebra on X, and since C is a collection of subsets of X, C would be a subset of P of X. So there is one. You could now, if you wanted, give a notation for the set of all sigma-algebras on X, which include all the sets in curly C. And as I say, that's a set of sigma-algebras. So that's a set of collections of subsets of X. And that would need a secondary degree of curliness that I'm not capable of writing. But I think I shall leave that there. You can now return to the original recordings of these sessions.